Today we're going to introduce the idea of apportionment, and I'm going to introduce it using this first example. In this example, we have a company that has 3 offices, one in Sacramento, one in Elk Grove, and one in Davis. The numbers here represent the number of employees each office has. And the situation we find ourselves in is we have 80 new computers. Question is, how many computers should each office get? Now, you may be thinking, can't we just divide it up evenly among those 3 offices? And the answer is yes. That is a possible answer. That's not the answer I'm looking for because there's one additional requirement. I want it to be based off of the number of employees at each office. In other words, if an office has more employees, I want that office to have more computers because they probably need it. If an office has less employees, they should get less computers. So the question is, how do we do this? How do you decide how many computers each office gets? And the first method we're going to talk about is a method I'm going to call the percent method. Because the first question we're going to ask is, Sacramento has 300 employees. What percent of the total does that represent? So to find out, I'm going to first need the total number of employees at this company. So 300 plus 75 plus 125. So add those up. And you can use any calculator. The calculator that I'm going to recommend is the Decimal Scientific Calculator. I'll put a link on Canvas for that. 300 plus 75 plus 125. And the total is 500. There's 500 employees total at this company. Sacramento has 300 of them. What percent is that? To find out, what we're going to do is we're going to take 300 and divide it by the total. So 300 over 500. 300 divided by 500. You should get a decimal. 0.6. That's a decimal. As a percent, what percent does that represent? This is a review of decimals and percents. The way you find out is take your decimal and basically multiply it by 100, which is the same thing as taking the decimal and moving it two places to the right. 1, 2. Okay, that's my new decimal. I'm going to fill in this space with a 0. That's 60 decimal, which is 60. So 0.6 as a decimal, 0.6, which is a decimal, as a percent, would be 60%. Sacramento has 60% of the employees. They should probably get 60% of the computers. Okay? So 60% of the computers, 60% of, how many computers do we have? We have 80 computers. What's 60% of 80? So to find out, you're going to do 60% times 80. But anytime you do arithmetic with percents, you always have to convert it back to a decimal. So 60% back to a decimal, right, which is divided by 100, or move the decimal 2 to the left, and you'll just get the decimal that we got at the beginning. So 0.6 is the decimal times 80. 0.6 times 80. 48. So Sacramento should get 48 computers. And now let's do the same thing for Elk Grove and Davis. So Elk Grove has 75 employees. What percent is that? So to find out, you can do 75 divided by the total. 75 divided by 500. You should get a decimal. 0.15. That's a decimal. What percent is that? So once again, convert the decimal to a percent by moving the decimal 2 to the right. 0.15. 2 to the right would be 1, 2. Okay, that's a new decimal point. That's 0.15 decimal, which is really 15. That's 15%. Elk Grove has 15% of the employees. They should probably get 15% of the computers. So 15% of the total number of computers, which is 80. 15% times 80. Once again, convert it back to a decimal. 15% as a decimal. It's just going to be the 0.15 that we got at the beginning. Times 80. Okay, 0.15 times 80 is 12. And then same thing for Davis. Davis has 125 employees, so 125 out of 500. That's 0.25. 0.25 as a percent, move it the decimal point 2 to the right. That will get you 25. Okay, Davis has 25% of the employees. They should probably get 25% of the computers. So 25% of 80. Convert the 25% back to a decimal. That's 0.25 times 80. 0.25 times 80 is 20. And there you go. So we're saying Sacramento should get 48 computers, Elk Grove should get 12 computers, and Davis should get 20 computers. Okay, does this make sense? Sacramento has the most number of employees. They got the most number of computers. Elk Grove had the least number of employees. They got the least number of computers. Okay, that part makes sense. Just to double check, let's make sure that we used up all of the computers. So 48 plus 12 plus 20. I expect this to be 80, right? I expect this to be all of the computers. So 48 plus 12 plus 20. It is 80. So it looks like we're good. Now, this example, I was very careful to pick these numbers so that everything works out very nicely. Now, in reality, you're never going to get very nice numbers like this. Okay, so the question now is, what do you do when the numbers are not nice? Example 2. A delivery company employs 71 delivery drivers. The company assigns each driver to one of the 4 regions based on the number of packages that need to be delivered in each region. We have north, south, east, west, and these are a number of packages that need to be delivered in each of those regions. The question is, how many drivers should each region get? And I want to base this off of the number of packages. So if a region has more packages that need to be delivered, they probably need more drivers. And the idea is going to be the same as in example 1. I'm going to first ask myself, what percent of the packages does the north have? They should probably get that percent of the drivers then. So to find out what percent, I need to first find the total number of packages, which I'll get by adding up those numbers. 261 plus 514 plus 766 plus 1019. And we have 2,560 packages total. The north has 261 of them. What percent is that? Okay, so we'll take 261 and divide it by the total. So 261 divided by 2560. You should get a decimal, and this time you should get a decimal that is not nice. Okay, so you'll get a long decimal. So let's agree that anytime we work with decimals here, let's round to 3 decimal places. So rounded to 3 decimal places, this is going to be 0.102. That's as a decimal. What percent is that? So 0.102 as a percent, multiplied by 100, which is the same thing as moving the decimal point 2 to the right. So 2 to the right, you'll be at 10.2. The north has 10.2% of the total packages, which means they should probably get 10.2% of the drivers. So 10.2% of the drivers. How many drivers do we have? 71. 10.2% of 71. Anytime you do calculations with percents, you always have to convert it back to a decimal. So 10.2% as a decimal will just be that 0.102 that we got at the beginning times 71. 0.102 times 71. 7.242. So this doesn't really make sense. Okay, we're talking about how many drivers should the North get. So this is telling us that the North should get exactly 7.242 drivers. Doesn't make sense because what's 0.242 drivers? Right? You can't have 0.242 drivers. So this is really the problem with apportionment. So in apportionment, what we're doing is we're sharing a resource. In this case, we're trying to share 71 drivers. In example 1, we were sharing 80 computers. Okay, and notice that these things, the computers and the drivers, we can't cut up, right? So I can't cut up the number of drivers to be exactly 0.242. So the apportionment problem, we're sharing a resource, and that resource can't be cut up. That's really the issue here, right? We're trying to share a resource that can't be cut up. And we're also sharing based on something. In this example, we're basing it on the number of packages that need to be delivered. In example 1, we're basing it on the number of employees. Okay, so that's really the apportionment problem. We're trying to share a resource that can't be cut up, right? A resource that has to be a whole number, and we're basing it off of something. Okay, either number of packages, number of employees, or a number of something. So the question is, how do I deal with a decimal? What do you do? So I'll let you think about that for a moment. And let's continue on the calculations, okay? For the South has 514 packages. What percent is that? So we'll take 514 divided by the total, 2560. 514 divided by 2560. Okay, you'll get a decimal. It's a long decimal, so round it to 3 decimal places. So rounded would be 0.201. So I'm going to be lazy here because I notice now that, right, we start with a decimal, we convert it to a percent, and then we have to convert it back to a decimal before we multiply. So let's be lazy here and not convert it to a percent. So let's keep it as a decimal and just take the decimal and times it by the number of drivers we're trying to share. 0.201 times 71. $14.271. Okay, so even though I'm being lazy, you should still like logically think that the idea here is that the South 0.201, right? As a percent, that's 20.1%. So the South has 20.1% of the packages, which means what we're doing here is we're trying to figure out they should get 20.1% of the drivers. And this is what we're calculating here. 20.1% times 71 is 14.271. So the South should get exactly 14.271 drivers. We know it doesn't make sense, the decimal part. We'll figure out what to do with that later. But they should get exactly 14.271 drivers. And then let's do the same thing for East and West. Okay, for these, I'm going to fast forward the video here, but feel free to pause it and do the calculations and then check your work with me at the end. All right, so go ahead and check your work and make sure you're getting the same answers that I am. So these are exactly how many drivers each of those regions should get. So the North should get 7.242 drivers. Now, let's decide on what to do with these decimals. What should we do with these decimals? What do you think? So you might be thinking round. Okay, I accept that. Let's agree to round. So 7.242 will be rounded to 7.242 is rounded to what? 7. So let's give the north 7 drivers, the south 14.271 rounded to the nearest whole number, 14. We'll give the south 14. The east 21.229 rounded to the nearest whole number, 21. The west 28.258 rounded to the nearest whole number, 28. Okay. Looks like we're done, right? Let's double check. The west had the most packages, so they should probably get the most drivers, and they do. The north had the least number of packages. They should probably get the least number of drivers, and they do. And now, just to double check, let's make sure that we used up all the drivers. 7 plus 14 plus 21 plus 28. Okay, I expect it to be the 71 drivers. Is it? 7 plus 14 plus 21 plus 28. 70. That's a problem. I expect this to be 71, right? So, which means I have one extra. I have one extra driver left. Who do you give it to? Who do you give this extra driver to? Okay, so on a lab, I'm going to ask you to answer that question. There's no right or wrong answer. Just based on your opinion, who do you think should get the extra driver? North, south, east, or west? Okay, based on the entire situation, right? If you were like the manager of this delivery company, who would you give the extra driver to? Who would you assign the extra driver to? North, south, east, or west? Once again, there's no right or wrong answer. I just want to know who you would give it to and why. What's your opinion on who should get this? Example 3. A transportation company operates buses in Boston, Chicago, and Sacramento. The company needs to distribute 83 buses among the 3 locations based on the number of riders. These are 3 cities, and these numbers are the number of riders in each of those 3 cities. And the question is, how many buses should each city get? So the apportionment problem here is we are sharing 83 buses. So we're sharing a resource that can't be cut up, right? It doesn't make sense to cut up a bus. So the number of buses we give to each location is going to have to be a whole number. And we're sharing the buses based on the number of riders. Okay, so that's our apportionment problem here. So for this problem, I'm going to speed up the video and work out the problem. So feel free to pause it, work it out, and then check your answer with me at the end. So to start, I'm going to need to find the total number of riders for these 3 cities. All right, so these are the answers I'm getting. Hopefully you got the same answers. If you got different answers and you don't know why, make sure you ask me. So what we just found out is that Boston should get exactly 33.698 buses. Chicago should get exactly 42.662 buses. And then Sacramento should get 6.64 buses. Now, once again, it doesn't make sense to have 0.698 buses, so we do have to round here. So how should we round? So 33.6, right? That means I should round up. So Boston should get 34 buses. Chicago should get 42.662 rounded to the nearest whole number. That's going to That 0.6 is going to bump it up to 43. Sacramento, 6.64 rounded to the nearest whole number would be, that would bump it up to 7. Okay, so Boston, Chicago had the most riders, so they should get the most buses. We're good. Sacramento has the least number of riders, so Sacramento should get the least number of buses. We're good. Now let's check that we use the right number of buses. We have 83 buses total, so let's make sure that we actually use 83 buses. 34 plus 43 plus 7. Okay, I expect it to be 83, and it's not. So it looks like we're using too many buses here. We only have 83 buses. These numbers tell us we're using 84 buses, which means we have to take away a bus from somebody. Who do you take away the bus from? Do you take away from Boston, Chicago, or Sacramento? So in the lab, I'm going to ask you to make a decision. Boston, Chicago, Sacramento, who do you take the bus from? And why? There's no right or wrong answers there. Just tell me who you take the bus from and then give me a reason why. All right, so I think that's it for today. So this is an intro to the apportionment problem. In the lab also, I'm going to ask you to think of other situations where you have to share something that you can't cut up. So that will be one of the problems on the lab. Have a great day. I'll see you next time.